Okay, radioactive decay. Some of it's a recap on stuff we did last year, but most of it's new information. So here are 3 things that we're trying to learn. Number 1, why are some atoms radioactive? Fairly simple to explain, we'll talk about that in a minute. Number 2, what are the 3 types of nuclear radiation made of? So last year we learned about the existence of alpha, beta and gamma radiation. Today we'll learn what they actually are. I don't know what, when we talk about them, you've probably got a picture of something in your head. Today we'll learn what you should actually be picturing. And then number 3, how can we write equations to represent different types of decay? Looks complicated at first glance, but actually with a little bit of thought is a very, very straightforward thing. So let's get a move on with the first one. Why are some atoms radioactive? So you're all familiar with a periodic table. Here is one right at the top, hydrogen, helium number 2, all the way down to, I don't even know the names of some of these, uranium, plutonium, americium, various ones down there. Okay, so why are some atoms radioactive? Well, it's all to do with the nucleus. So inside the nucleus of any atoms are protons and neutrons. Protons, as you know, are positively charged. Neutrons have no charge at all. So all those protons are positively charged and are therefore all repelling each other. So how is it that the nucleus stays together? Well, there is something called the strong nuclear force, and it's the strongest force in nature, and it is able to overcome that repulsion and hold the nucleus together. Okay. Now, although the strong nucleus is very, very strong, it only acts over a very short distance. So, as long as you're talking about small nuclei, like the hydrogen nucleus, which is actually just a proton, or the helium nucleus, which is 2 protons and 2 neutrons, then that's fine. That strong nuclear force can hold that nucleus together. As you go along the periods, down the groups, we start to get more and more protons in the nuclei, as you can see by the number. 21 protons, 22, 23, etc. The number of protons gets higher, and the number of neutrons gets even higher than that. Okay, so these, when we get down to these atoms down here, they are very, very big nuclei with a lot of protons and a lot of neutrons, and the strong nuclear force finds it harder to hold those nuclei together. Some of them are so big that they are unstable, and like all unstable things, they will eventually revert to a more stable state. That's what we call radioactive decay. It's just an unstable atom reverting to a more stable state. Now, if you think the reason they're unstable is basically they have too many neutrons, how do they become more stable? Get rid of some neutrons. So when we say an atom emits alpha radiation, it emits beta radiation, or it emits gamma radiation, what we're saying is that that atom is getting rid of some neutrons, and in so doing is becoming more stable. Okay? So, why does an atom undergo radioactive decay? Because it's unstable. Because it's got too many neutrons, so it gets rid of some. Simple. So now we'll look at the 3 individual types. Starting with alpha decay. Okay, so here we go. What is alpha decay? Well, here is your unstable nucleus. You can see it packed full of neutrons and protons. Okay, very unstable, can't exist in that state. So it needs to get rid of some protons and neutrons. Here is it doing it. It emits an alpha particle, which hopefully you can see from the diagram is made of 2 neutrons and 2 protons. So when we talk about alpha radiation, that's what we're talking about. It is actually 2 neutrons and 2 protons that have been ejected from the nucleus of an atom. And if you think about what we talked about on the last slide, this nucleus is now more stable. It has fewer neutrons and protons. The strong nuclear force therefore finds it easier to hold that nucleus together. So by ejecting an alpha particle, it has become more stable. You'll sometimes hear an alpha particle referred to as a helium nucleus, because it is a helium nucleus. If you ask your chemistry teacher, what's a helium nucleus look like? They'll tell you it's made of 2 protons and 2 neutrons. And if you ask a physics teacher what is an alpha particle, they'll say it's 2 protons and 2 neutrons. So an alpha particle and a helium nucleus are the same thing. Okay, so that's alpha decay. Pretty straightforward. Right, onto beta decay. So this one's a little bit more complicated and a little harder to remember, but the general idea is the same. This nucleus has too many neutrons in it. It needs to get rid of some neutrons so it will become more stable. And it does this in an interesting way with beta decay. Okay, so one of these protons spontaneously changes into, one of these neutrons spontaneously changes into a proton and an electron, and the electron is fired out. So a neutron changes into a proton and an electron. Okay, so just like before, there are now fewer neutrons than there were, and the thing that we talk about as beta radiation is in fact the electron that was ejected from the nucleus. There it is. So if in the exam you're asked what is a beta particle, you would say it is a high-speed electron. They go very, very fast. Okay, simple. And then finally, gamma decay, which is dead easy, as it's not a particle at all. It is, of course, an electromagnetic wave, and it doesn't actually change the structure of the nucleus at all. It just allows it to release some energy. So gamma decay usually happens alongside alpha decay or beta decay. Okay, so what are the three types of radiation? Alpha, beta, and gamma. What are they? Alpha decay is 2 protons and 2 neutrons, sometimes called a helium nucleus. Beta decay is a high-speed electron, and gamma decay is a electromagnetic wave. Simple. So the final bullet point was, how can we write equations to show what happens during alpha, beta, and gamma decay? And that's what we're going to move on to now. So, at first sight, that equation might look complicated, but actually it's very, very easy. So if we think about our alpha particle up here, here it is, you can count very easily that alpha particle has a mass number of 4. That's 2 protons plus 2 neutrons gives it a mass number of 4. And it has an atomic number of 2. 2 protons, atomic number 2. Okay, and that alpha particle is going to come out of the nucleus of an atom. Okay, so here is our radioactive uranium atom down here. Okay, it is about to, once it undergoes alpha decay, it spits out an alpha particle. Therefore, its mass number will decrease by 4. Okay, and because it's just spat out 2 protons, its atomic number will decrease by 2. Okay, so 238 becomes 234, and 92 becomes 90. Very straightforward. Of course, we have to make sure that both sides of the equation balance. So you can see the total mass over here, 234 plus 4, is the same as the total mass over here, 238. Same with atomic number. 90 plus 2 over here is the same as 92 over here. It balances. Okay. Now, you're probably noticing, or I hope you're noticing, that this uranium atom seems to now be a thorium atom. A bit strange, you might say, but actually not when you think about it. If you look at your periodic table, which I have no doubt you have hanging on your bedroom wall, you'll notice that each element has an atomic number, that is the number of protons, and it is that number of protons that defines an element. The only difference really between a carbon atom and a nitrogen atom and a gold atom is the number of protons in its nucleus. So when one element, uranium, loses some protons, it can no longer be uranium. It has a different atomic number, and in this case it becomes thorium. So during radioactive decay, elements become other elements. If you had a lump of uranium and you left it for a very long time, eventually you wouldn't have to do anything at all. Eventually you would end up with a lump of thorium. Okay, so that's alpha decay. Mass number goes down by 4, atomic number goes down by 2. Simple. Beta decay is a little bit harder to remember, and the way you remember it is by remembering this is your beta particle, a high-speed electron. Where did that electron come from? Okay, so you have to remember that it was a neutron changing into a proton and firing out an electron. So the electron we don't need to worry about too much. It gets shot out of the nucleus. Here it is, and it's written here, okay, as a beta particle. You might see it written as that. It doesn't make any difference, they're the same thing. Okay. So, we have exchanged a neutron for a proton. We have exchanged a particle with a mass of 1 for a particle with a mass of 1. Neutron, mass 1, proton, mass 1. So the mass number in beta decay does not change. Okay, there you go, 14 on both sides. Okay, but we have gained a proton, where before we had a neutron, now we have an extra proton. So the proton, or atomic number, has to go up by 1. Okay, and just like before, once you change the number of protons, you change that element. So this radioactive carbon-14 becomes an atom of nitrogen. Okay, so that's beta decay. I think the key to remember in beta decay is where does the beta particle come from, and it's a neutron changing into a proton. Once you remember that, working out the numbers is pretty straightforward. And then, here we go, gamma radiation. You'll notice gamma radiation has a mass of 0, and atomic number is 0. Okay, therefore it can have no effect on the structure of the atom. And as we said before, gamma decay just happens alongside alpha or beta decay and allows the atom to lose some energy. Okay, pretty straightforward. The final slide is just a little true or false activity for you to check. Have you understood everything we wanted to talk about? Okay, pretty straightforward. Have a go at it. We'll go through it in class as well and check that you've understood. Okay. Obviously, if you're not sure that you have met all those objectives, then just go back through the video and listen again. Okay. Thank you.